Hi everyone, this is the second lesson of Physics A-Level Waves. This is diffraction and superposition. This lesson will cover diffraction, interference and the principle of superposition, the difference between constructive interference and destructive interference, and then some key ideas of coherence, path difference and phase difference. And the context example for this would be noise cancelling headphones, which are becoming more and more popular. The way they work is they monitor the ambient sound around the person listening and then flip the sound 180 degree out of phase and combine the two sounds, and then destructive interference will effectively, or fairly closely, cancel each other out. You're probably familiar with the idea of diffraction from GCSE physics. So the way we describe this is the spreading out of a wave after passing through a gap. So we've looked already at representing waves with this wavefront idea. So remember, each one of these lines could be the peak. So let's say peak to peak, so the gap between these two lines is the wavelength of the wave, and the wave moves towards a gap and then spreads out. So we get this maximum effect of diffraction, as shown here, when the wavelength is approximately the same size as the gap that the waves are passing through. If we increase the size of the gap, we get a reduced amount of diffraction. So we still get diffraction, but it's not quite as much. And then the bigger the gap, well, it starts to almost diminish to zero. Most of the wave just goes through unchanged. We get a little bit of diffraction at the end. So generally speaking, in Physics A level, we're talking about waves passing through a gap. We also get a bit of this effect when waves pass around an object, which is comparable size to the wavelength, and then that wave will bend around the edge. Lots of examples and applications, so CDs or DVDs reflecting all the colours of the rainbow, that involves diffraction. We get a red colour during sunsets, a spectrometer, which we might look at later on in this topic, separating white light using a prism, holograms, light bending at the corner of doors, X-ray diffraction. So this is used a lot in science and research, and there's a lot of examples of this in the real world as well. So the principle of superposition, this is something that you need to know for the exam. When two or more waves meet at a point, the resultant displacement is the sum of the displacements of the individual waves. So we normally talk about this when two coherent waves meet. So if we have coherence, then the two waves are identical. They have the same frequency and the same wavelength. However, the definition we use for coherence is two waves with a constant phase difference. So that might be a constant phase difference of 0 if they start at the same point, or 180 degrees if they start half a wavelength out. But there is no change in that phase difference. So very often coherent waves are produced by the same source. So for example, you might have two loudspeakers both connected to the same signal generator, and the waves are coherent as they're produced from the loudspeaker. So the two extreme scenarios, and the ones we generally talk about, are constructive interference and destructive interference. So if the two waves, both coherent, meet in phase, which means their phase difference is 0, then they add up to make a wave which has got twice the amplitude of the original wave. So the amplitude increases. The other extreme is if the phase difference is 180 degrees, so anti-phase, and then they cancel out effectively. So if we have a peak meets a trough, that cancels out to give 0, trough meets a peak, and so on. So these are the two extreme cases, but we do get superposition even when the waves are not coherent. And this is used in synthesizers to produce complex sounds, artificial wave sounds, which the brain thinks is a trumpet or an acoustic guitar or whatever it might be. And we can add multiple waves together of different frequency and amplitude and phase difference to make far more complex waves. We're going to talk about an example of the principle of superposition, which you may well have seen demonstrated in a science lesson, and it's often talked about in exam questions as well. So it's quite an easy one to set up. You could probably do this yourself at home if you want to. You need two loudspeakers, both connected to the same source, and we normally just use a simple sine wave of a particular frequency. So it's a pure sine wave, a particular frequency being produced. So if a person walked along in front of these two speakers, what they would hear is a series of loud and quiet sounds. Now, it wouldn't be totally quiet because you've got a lot of reflection around the room, but what is effectively happening is where those two waves, so the wave from the left speaker and the wave from the right speaker, where they meet in phase, we get constructive interference, so we hear a loud sound, and where they meet out of phase, we get destructive interference, which is a quiet sound. So we need to be able to explain this in terms of path difference, in terms of how many waves have actually travelled. So this is a side view, or maybe a top view, of what we've just talked about. So we've got two loudspeakers. They're both producing the same type of wave, a coherent wave. So if you're in the midpoint of these two loudspeakers and you stand here, you will hear a loud sound. If we look at the number of waves, we've actually got 5.5 waves have travelled from this speaker here, and 5.5 waves have travelled from the speaker at the bottom. So they started off in phase, they've travelled the same distance, so their path difference is 0. So they're in phase with each other at this point. So we'll get constructive interference, we'll get maximum amplitude, and we'll hear a loud sound at this point. If we consider a point as shown here, which is in front of one of the speakers, so we have the same wave format as we had previously from the one at the top. The one at the bottom, these waves now have to travel a little bit further. So they've travelled a greater distance, so they're no longer going to be in phase in this particular example. And if we count how many waves here, we've got a total of 7 full waves compared to 5.5 waves. So we have a difference of 1.5 waves. The path difference is 1.5 waves. So now these two waves are going to meet out of phase, 180 degrees out of phase, known as antiphase. So here we get destructive interference, and effectively the waves cancel out and we get no sound at all. Okay, now it's your turn to put this into practice. So have a read of the questions, pause the video, and then try to answer these as best you can. Question 1 is the basic description and notes. So this idea of loudspeakers that we've mentioned is a really common question in the exam. It's a nice illustration of constructive and destructive interference. So we could talk about high and low volume. A better word would be intensity, as shown here. As we've said, where the waves meet in phase, we have constructive interference, and where they meet in antiphase, 180 degrees out of phase, we get destructive interference. You do need to know the principle of superposition. So when two or more waves meet at a point, the resultant displacement is the sum of the displacements of the individual waves. So note it's not amplitude, it's the displacement at that point. And then coherence or coherent is constant phase difference. You have to be careful here because very often students write they have the same frequency, the same wavelength. Well, they do, but that's not the definition, that's not what the examiner is looking for. Okay, question 2. So you may well get a question similar to this where you actually have to think about how far the waves have travelled and then work out, knowing the wavelength, whether they're in phase or out of phase. So we know that if we have student A in position A here, then the distance, if that's in the middle, then the distance the waves have travelled from each of these speakers, left and right, is going to be the same. We assume it says an identical sound, so we assume the waves are coherent. So if they've travelled the same distance, they're both going to be at the same point in their wave cycle, whatever that is. So it's going to be a loud sound. And the detail we need is the waves travel the same distance, so they are in phase, and we get constructive interference. For part B, a little bit more tricky. So as we said before, if we're directly in front of one of the speakers, then the distance the waves travel from the left and the right speaker is going to be slightly different. So we know that this is 2.4. As the hint in the question says, we're going to have to calculate the hypotenuse of this right angled triangle. And we can do that, it comes out as 4 meters. So what do we do with these two numbers? We have 4 meters and 2.4 meters. So the first thing we can do is to calculate the path difference, the difference in these two distances. So 4 minus 2.4 is 1.6. And we're told in the question that the wavelength is 1.6. So the difference that the waves have travelled is a full wavelength in this case. So they are now back in phase. So we get constructive interference. so we hear a loud sound. So without the numbers, we couldn't have assumed that it would be loud or quiet. We wouldn't know. We need to know how far have these waves travelled in order to work out the path difference, and then to work out whether they are in phase or otherwise. Okay, so a quick recap of this lesson. Just have a read through these 6 questions, pause the video, and just check you have the answers to each of these. Okay, so diffraction, the spreading out of a wave after passing through a gap. You could easily be asked that in the exam. The conditions for the most diffraction. They could ask you this, and this is very important for later on in the waves topic. So we get the greatest amount of diffraction when the gap or the obstacle size is the same size as the wavelength. Principle of superposition, you absolutely need to know this. It's probably a 2-mark question. When two or more waves meet at a point, the resultant displacement is the sum of the displacements of the individual waves. The meaning of coherence, constant phase difference. So be careful. If you write same frequency, same wavelength, identical waves, you won't get a mark. Constant phase difference. So what is constructive interference? So we need to be able to describe that. It's easy to see it visually. So the waves add together to create a large or maximum amplitude when the phase difference is 0 or when the 2 waves are in phase. Destructive interference at the extreme end is where we get 0 amplitude, 0 displacement all the way along the wave. That is when we have antiphase or 180 degrees. So for this lesson, there's probably not any exam questions other than just what we've considered already, so fairly straightforward questions and the definitions. So there won't be any exam questions on this particular lesson. The exam questions will lend themselves to the lessons later on in the topic. So this lesson is finished. Bye for now.